Welcome to the third part of this chapter on volumes of revolution. In this last segment, we will take a look at a new method called cylindrical shell. So as we've seen previously, when a rectangle is positioned parallel instead of perpendicular to an axis of rotation, and when this rectangle is made to revolve around it, then we actually get the following picture. The shape of the right-hand side can be construed as a tube or an empty shell, or perhaps like the shape of a paint can that is empty. So let's imagine what happens when we actually cut this tube along its vertical axis. When you unfold it, well, you'll get this box. Clearly, the height of the box is the same as the height of the cylinder. But what happens when we actually try to find the height of this box? Well, what happens when you unfold a circle? You get a line whose length is equal to the diameter of the circle. Hence, the length of the box is 2 pi r, and the volume of the box is given by 2 pi r times h times delta x. Since the volume of the box equals the volume of the tube, which we also call a cylindrical shell, we have that the volume of a shell is 2 pi big R h times delta x. Using a similar argument as in the case of disks, we can say that the entire volume of the cylinder can be obtained by summing up all the volumes of all the infinitely small shells, giving us the volume is actually equal to the limit, as then goes to infinity, of the summation, I equals 1 to n, of 2 pi rh delta x. But of course we know that this is the same as the integral of 2 pi big rh dx. To illustrate, consider the following rectangle of height h and length x. When this surface revolves around the y-axis, we expect to have a cylinder. Its volume should actually be, well, the integral of 2 pi rh dx. Taking the 2 pi r, I get the integral of xh dx, since the radius is x. Integrating xh dx with respect to x, we get 2 pi x squared over 2 times h, which is pi x squared h. Now it is interesting to notice that if we put the bounds in this integral, put the bounds to be from 0 to big R, we get that x squared h between 0 and r is pi r squared h, which is the formula for the volume of a cylinder. As a second example, let us actually calculate the volume of the region described below, which is nothing else than a triangle in the first quadrant, when it is actually revolved around the y-axis. So we want to practice our cylindrical shell method, so we'll position the rectangle once again parallel to the axis of rotation. So for this method, we basically need to identify two things, as you probably have noticed so far: big R and h. As we have seen before, the radius r corresponds to the distance between the rectangle and the axis of rotation. Since the distance will change depending on where we position the rectangle, we will actually call it x, since it's an unknown displacement along the x-axis. Now, what about the height of the rectangle? Well, just like in the case of area calculation, it can be construed to be just y high minus y low. But what is y high? We're not given y high here. Since y high is on the red line whose equation is not given, we will actually need to find the equation of the line. We actually know that this equation passes through 2 points, namely 0 big H and little r 0. Hence, its slope is 0 minus big H over little r minus 0, which is minus big H over r. Since the y-intercept is already known to be big H, we get the equation y is equal to minus big H over little r times x plus big H. Since y high is precisely the equation of that line and y low is 0, we're going to get that the volume is going to be the integral of 2 pi rh dx, which will be with the 2 pi outside. The radius is x, and the height is the y of the line. So minus big H over little r times x plus big H. So this is a dx integral. So let's put the bounds and let's integrate. The bounds are 0 from little r. Hence, let's integrate this with calculations we know. Taking the 2 pi out, we get the integral from 0 to little r of x times minus big H over little r times x plus big H dx. Multiplying the x in and integrating, we actually get minus big H over little r x cubed over 3 plus big H times x squared over 2 between 0 and little r with my 2 pi outside. So I use FTC part 2, I plug in my upper bound, I plug in my lower bound, and soon I find that I get pi r squared h over 3, which you may recall is the formula for the volume of a cone. Indeed, when one actually spins this triangle around the y-axis, one gets a cone opening towards the negative of the y-axis. Very good. Now the advantage of shells, over disks can actually be best illustrated in the next example. Let's try to find the volume of the region bounded by y is equal to x squared, y is equal to root x, revolving around the y-axis. We're showing the region here with the upwards parabola and the usual shape of the square root. The points of intersection are going to be needed, so letting x squared is equal to root x, we square both sides, we actually take out an x, and we get that 0 and 1, two nice points, are the intersects for these two curves. If we wanted to use disks on this, we would have to extend the horizontal rectangle all the way to the axis of rotation, hence creating big R and little r. But here, using shells is actually simpler. You put one rectangle parallel to the axis of rotation, and we get that big R is actually x, since the distance from the rectangle to the axis of rotation is the radius, and the usual height is y high minus y low when the rectangle is vertical. So in this case, the rectangle goes from the root to the parabola, so root x minus x squared. So we apply the formula integral of 2 pi rh, and we get the integral from 0 to 1 of 2 pi x times root of x minus x squared. Take out the 2 pi, multiply the x in, integrate with respect to x. The bounds are 0 to 1. Use FTC part 2 and plug that in, and we actually get 3 pi over 10 cubic units for this problem. Now, what if the same region was actually revolving around the x-axis? Here, the rectangle across the region should be positioned horizontally if we are to use the shell method, because the shell method requires the rectangle to always be parallel to the axis of rotation. So once again, we ask the same questions: what are big R and little h? Since the rectangle is horizontal, the height is no more y high, y low, but rather x right minus x left. That is to say, x right is on the parabola, so we isolate x, we get root y. X left is on the root, so we isolate x, we get y squared, so that h is root of y minus y squared. Now, what about the radius r? By design, it corresponds always to the distance between the rectangle and the axis of rotation. This is now a vertical displacement, So any distance from the x-axis to an unknown point is y. So we're going to let here the radius equal to y. Hence, we get that the volume is actually equal to, again, the integral of 2 pi rh. This time, it's a dy integral. So the bounds are yet again 0 to 1. So this is 2 pi, the radius is y, the height is root of y minus y squared dy. We bring in the y inside and we bring the 2 pi outside. We integrate, we apply FTC part 2, and we get once again 3 pi over 10 cubic units. So in the next example, we will actually set up the integral using shells that gives the volume of the solid when the region bounded by y is equal to x minus 2 all squared and y equals x is actually being made to revolve around different axes of rotation. First, let's sketch the region in the Cartesian plane. So what we have here is for y is equal to x minus 2 all squared, we have an upwards parabola with only one x-intercept at 2. That's my intercept right here at 2. While the equation y equals x is simply a line that goes through the origin. The points of intersection can easily be found to be 1, 1 and 4, 4. We will leave this as an exercise. So now we let this region revolve around the following axes. Let us start with the first example with the y-axis. So here our radius, big R, is again the distance between the rectangle and the axis of rotation as it always is. That big R is x, while h is given by y high minus y low because the rectangles are again vertical. That is from the line to the parabola, so x minus 2 all squared. So using shells, we get that the volume is 2 pi, the integral from 1 to 4 of x times x minus open bracket x minus 2 squared dx. As a second case, let's revolve this around the rotation axis. X is equal to 4. The distance here from the rectangle to the y-axis, again, is x. And now since x plus big R is 4, we have that the radius has to be 4 minus x. The height is the same as in the previous case, so that the volume is actually written as 2 pi the integral from 1 to 4 of 4 minus x times, again, the same height, x minus 2 squared dx. Now, one more example, this time revolving around x is equal to 1. Here again, the distance from the rectangle to the y-axis is x, but if we look at the picture, we see that 1 plus the radius is equal to x, so that we have the radius to be x minus 1. The height does not change, it's still y high minus y low, so the volume is 2 pi outside, the integral from 1 to 4, my radius is x minus 1, and my height is the same as usual. As one last case, let us consider revolving around the axis x is equal to -1. The diagram actually shows that here the radius is x plus 1. We could also look at this from a different angle. We could say that the radius is actually x right minus x left. So x on the right and -1 on the left gives us x minus -1 or x plus 1. Either way, the radius is x plus 1 and the height does not change, so that we actually have the volume to be the integral from 1 to 4 of x plus 1 times the usual height x minus 2 all squared dx with the 2 pi outside. To summarize, let's keep in mind here that for the shell method, we always want to position the rectangle parallel to the axis of rotation. And we should keep in mind as well that the radius r is the distance from the rectangle to the axis of rotation. And this concludes this segment.